Thanks so much, and good morning, everyone. As a reminder, if you're willing and able to turn on your camera to make it a little more pleasant for all of us, I super appreciate it. Thank you so much, everyone. So welcome to lecture number 2 on dark matter. And let me just briefly give you our outline for today. So basically what we did yesterday was talk a little bit about introduction to dark matter. I gave you an earlier universe cheat sheet, and then we started working through mechanisms. And in particular, we started working through the WIMP. And what we're going to finish off today is 2 to 2. Sorry, let me do that in another color. So we're going to finish off the WIMP today. So we're going to finish off the 2 to 2 WIMP, and then we're going to move to some other 2 to 2 processes. We're not going to work through all of those mechanisms and processes that I wrote out, but we're going to work through a few of them. And once we finish with 2 to 2, we're actually going to move to higher point interactions. So we're going to talk a little bit about 3 to 2 interactions. And in this context, we're going to see simps, and we're going to see cannibals, and we're going to see elders. And maybe more. My guess is that we're going to get somewhere inside this region, maybe something like this today, but we'll see at what pace we progress. So our first piece of business is to finish off the WIMP. So we worked together yesterday through, we wrote out we understood what the process was, we wrote out the Boltzmann equation, and we understood how the Boltzmann equation is supposed to be solved. We saw the standard picture for freeze out. And what we then went ahead to do was sort of do a back of the envelope estimate to understand when is freeze out occurring, what size parameters are we pointed to, and we arrived at a cross section that was of order an electroweak cross section, which is why the WIMP was given its name. And what I'd like us to do now is actually do a different alternative back of the envelope estimate, because this one is going to be actually super useful, as you'll see, for I want to sort of phrase the WIMP in a very particular way that's going to be very useful for us moving forward. Okay, so that's what we're gonna do now together. We're gonna perform an alternative back of the envelope. And I'll remind you that one of the things that we've been doing is redshifting. And the trick that I want to use now, and this is going to be a very, very useful trick throughout everything that we do together, is to redshift through T equality. Okay, so we're going to redshift to T equality, which is at around 0.8 eV. This is matter radiation equality, the temperature at which the energy density sitting in matter equals the energy density sitting in radiation. Okay, and so just sort of to warm up our muscles. So I remind you that we have this 2 to 2 cross section that we denoted like this, sigma v, which was a stand-in for the part of what's going on in our collision term, the matrix element squared with all of that phase space integration, etc. And I'm just going to parameterize this. So this is, I remind you, we're talking about a WIMP. So here's my 2 to 2 diagram where I have 2 chi's, which chi is my dark matter that's annihilating into 2 of something else. And let me parameterize this cross section, because this is just an ordinary cross section. I'm going to parameterize it as some effective coupling squared over mass of chi squared. Okay, this is just in the spirit of being agnostic to what's sitting in this blob that's creating this process. I'm just going to parameterize the cross section this way. And once we'll go later, anytime you write down a particular model that realizes this mechanism, you can then map this cross section into the parameters of your theory. Okay, so this is our parameterization for our cross section. And now let's take a look for a moment. I said we're going to be using a trick of redshifting to T equality. So let's look at what happens at matter radiation equality. Okay, so at matter radiation equality, what happens is that the energy density sitting in matter, okay, at equality. So this, now when I'm writing EQ, this isn't equilibrium, this is equality. Okay, so this should equal the energy density that's sitting in the dark matter plus the energy density that's sitting in the baryons, right? And by definition, at equality, this equals the energy density sitting in photons. Okay, now let's go back to what we started off at the beginning of our lesson yesterday, which is how much dark matter we have in our universe today. And we know that we have roughly 5 times the mass density of baryons sitting in dark matter. Okay, and so what I'm going to do now, and this is the point where I'm sort of going to be ignoring order 1 factors. Okay, so roughly what I'm going to use here is that the energy density of dark matter at equality is up to this order 5 factor. The energy density sitting in photons. Okay, so what I'm doing right over here, I'm neglecting this order 1, but you can see how through what we're doing, if you wanted to trace it back to make things more accurate, you could, but for our purposes, this is going to suffice. Okay, so let's get to work. So let's start with the following. So what I want to get is, what is dark matter density at freeze out? Number density of dark matter at freeze out. And so let me now redshift this from freeze out to T equality. Okay, so this is going to be number density of dark matter at equality. And the way that I redshift is, as we saw, either by entropy ratios or by equivalently temperature cubed ratios. So let me just insert here, I have to redshift by T freeze out over T equality cubed. Okay, this is how I've redshifted from freeze out to T equality. Now, the number density of dark matter at equality is non-relativistic. And so, so if dark matter here is non-relativistic, then I remind you that rho equals n times m. And so the number density I can just write as the rho of dark matter at T equality over the mass of dark matter. So that's my number density. And my temperature factors, I'm just copying over T freeze out cubed over T equality cubed. Okay. And now let's use the fact that we're sitting at equality right now. And so the number density, sorry, the energy density of dark matter at T equality, like we just wrote, is of order the energy density sitting in photons. Okay, so let's use that. So here we're talking about at equality. So that's what I'm putting in over here, that we're at equality. And so I can now write this rho, instead of rho chi, I can write down rho photon at equality. The rest I'm just copying over m chi, T freeze out cubed over T equality cubed. Okay. Now my photons are just scale as T to the 4th, right? That's the energy density of relativistic particles. So we just have temperature to the 4th for the photon density. And so this is happening at T equality. And so I'm going to get temperature to the 4th, and I already have a temperature cube downstairs. So combined, I'm going to end up with T freeze out cubed, nothing changed. I'm going to have 1 factor of T equality over m chi. And one last thing that we're going to do is I remind you that we defined x to be m over t. And so I'm just going to move to this dimensionless quantity. And so what we've ended up with is T equality m dark matter squared over x freeze out cubed. This is a way for me to write down the number density of dark matter at freeze out in terms of T equality, where I've already, in order to get this relationship of what is the number density of dark matter at freeze out, I've already used the fact that this is the number density that gives me the amount that we've measured today, because we've already used how much dark matter we have in our universe today. Okay, so this is going to be a very important relationship that we're going to be able to use actually throughout many mechanisms. Okay. Number density of dark matter at freeze out equals T equality mass squared over x to the 3rd. Okay, so now let's compare this to our freeze out condition that we derived yesterday. So let's compare to our freeze out condition. And I think yesterday we gave it a name. It was this equation red star, and I'm just going to write it out, of course, here as well. So I remind you that what this equation was, it told us that the 2-to-2 rate, which was n chi times sigma v, had to be of order Hubble, and Hubble is T squared over m Planck. Okay, so let's write this out now explicitly. So here we have our 2-to-2 rate, scales like, so number density, this is exactly, this number density over here is what we just wrote out. Okay, so we're going to copy that over. So we're going to use T equality m chi squared over x freeze out cubed. That's my number density of dark matter. And our cross section, this cross section over here, this is what we parametrized. This is what we just parametrized over here. I'm going to use this parametrization of coupling squared over mass squared. So I'm going to insert that in now. So I have here alpha effective squared over m chi squared. And at freeze out, this rate should be of order Hubble. And as we just said, this should be of order Hubble at freeze out, which is temperature freeze out squared over m Planck. And again, I'm going to move to this variable x. So we're going to have here m chi squared over x freeze out squared times m Planck downstairs. Okay. And now all I have to do is shift around and what we're going to find and solve for m. Okay. And when I do this, here's what you get. And I'm going to be sloppy with my factors of mx because they're of x because they're not going to be crucial for me here. But what you find is that the mass of dark matter at freeze, given by our freeze out condition, goes like the coupling alpha effective times square root of T equality and m Planck. Okay. So this is what we get for a 2-to-2 annihilation process of the WIMP, which is responsible for the relic abundance of dark matter. We get that the mass scales like the coupling times a geometric mean between T equality and m Planck. And if you plug in the numbers over here, what you get is alpha effective times around 30 TeV. Okay. And so it happens to be the case that if this effective coupling is of order an electroweak coupling of order 10 to the minus 2, then the scale of dark matter that's pointed to is of order the electroweak scale of a few hundred GeV or of order a TeV. Okay, so if alpha effective is of order the electroweak coupling, then the weak scale emerges. Okay. And what I'd like to stress here is that this is a complete coincidence of scales. Okay, we have two completely unrelated scales, T equality and m Planck, that contrive together to give us a geometric mean, which if we put in a weak coupling gives us the weak scale. Okay, this is a coincidence of scales between T equality and m Planck. Okay. And so you see over here that the WIMP miracle, and this is why this type of process is called the WIMP, because if we plug in a weak coupling, then what happens is we get the electroweak scale. But there's absolutely no miracle here. This is a complete coincidence of scales. And in particular, even though this mechanism and this relationship for so long people have been focused on thinking about weak sized coupling, which gives us weak masses, I just want to point out that we see obviously very easily that if, for instance, this coupling is much smaller than 10 to the minus 2, then we naturally get dark matter masses that are much smaller than the electroweak scale. Okay, so this can also give us very easily light dark matter. The exact same mechanism, just looking at a different regime of the couplings. Okay, so this is our back of the envelope estimate, which gives us a relationship, a size of that cross section, or alternatively a relationship between the mass and the coupling, such that we get the amount of dark matter that we observe in our universe today. Now, another way to write this exact same relationship, and this is also going to be useful, so I'll just write this down. Another way to write this is that the size of the cross section, right, which we define to be alpha effective squared, over, this should be little m, over mass of dark matter squared. If I just take this relationship that we have over here, then you see that it tells us that the size of this cross section is exactly 1 over T equality m Planck. Okay, so this would be an alternative way to phrase the WIMP miracle. Now, also important over here is that, of course, one can worry, okay, we talked about I could take coupling to be much, much smaller, and then I get very light dark matter. And you can ask yourself, how heavy in dark matter masses can I go? And over there, we have to worry in principle about something called the Unitarity Bound, which tells us that if we're writing down a quantum field theory, then, roughly speaking, when we're talking about some couplings, we typically don't think of couplings that much exceed sort of the 4 pi value, right? The strong size couplings. And so if you were to naively say, okay, this alpha effective that we've parameterized our cross section with shouldn't exceed 4 pi, then what you would find is that there's an upper bound on your dark matter mass that's of order a few hundred, let's say 300 TeV. Okay, and this is what's called the Unitarity Bound. And this Unitarity Bound was originally derived by in a beautiful paper by Greist and Kamiokowski I'm for sure going to misspell Mark's name, Kamiokowski, back in 1989. Okay. Now, actually, recently, in recent times, there's actually been some activity in understanding how can one fairly easily actually exceed this unitarity bound. So it was often thought that you really just couldn't have dark matter masses that were heavier than 300 TeV if this 2-to-2 annihilation is what's setting the abundance. But there are actually ways to evade. So I'm just going to give you guys the references for this, but it's really awesome paper, so I recommend reading. So this is in contrast of ways to evade. So people have recently worked out thermal relics, okay, relics of dark matter that are in thermal contact with the standard model in the early universe that have mass that exceeds this bound of a few hundred TeV by, so far, I think the literature has maybe up to 12 orders of magnitude. But we believe it's actually going to be possible to go even all the way up to the Planck scale. And I'll just give you a couple of cool references to read for this. So the first is a paper that's called Super Heavy Thermal Dark Matter. And this is a nice PRL by Koflik and Kim, a PRL that's 1906.00981. So this is one way, and what this actually uses is a long chain of nearest neighbor interactions. Okay, so this is a chain of nearest neighbor interactions. And the second one, which is also a very nice PRL, is one of the pictures that we drew for the processes. It's the zombies paper, and this is a paper by Kramer, Koflik, and many others. And this is, again, a nice PRL, and I'll give you here the reference, 2003.04900. Okay, and what this one uses is that zombie process that we drew. Okay, and so there are ways to also go to higher masses. Okay, and so sort of bringing all of this together, what we find combined for the WIMP is that, if we think about what's the range of dark matter that we can have, you can kind of think of this as, let's say, the keV scale and above. Going lower than keV can sometimes be problematic. We're going to discuss constraints probably either tomorrow or the day after. And roughly, again, may be bounded by 300 TeV, but plus, of course, these caveats of ways to evade. Okay, so this is the WIMP, and this is what was really the dominant focus of the dark matter community for many years. And what we're now going to move on, that we finished the WIMP, is to other processes, okay, other mechanisms. So our next mechanism within the 2-to-2 zoo, if you remember, we drew a lot of different processes. The next one that I want us to work through together are forbidden channels. Okay. Okay. So forbidden channels actually has a pretty interesting history. So it was actually originally proposed, but in the context of the WIMP, by a very nice paper by Grist and Seckel back in 1991. And it's sort of been rejuvenated or revived in the context of light dark matter more recently by, so the original paper for that is by Josh Ruderman and Raffaele Dagnolo in a nice PRL that is 1505.07107. Okay, so here's the process. Let's look at exactly the same process that we've been talking about so far. 2-to-2 interactions where chi's annihilate into phi's. Okay, but now let's look at the kinematic regime where the mass of chi is smaller than the mass of phi. Okay, so if I was looking at this at 0 temperature, this process would be forbidden, right? If I'm trying to remind you that time in our lectures together is going in this direction. And so if the sum of the incoming masses is smaller than the sum of the outgoing masses, then in the absence of some temperature, some bath that's providing some extra energy, this process just cannot occur, okay? But fortunately for us, the early universe is a thermal environment, okay? And so in the early universe, this process can happen by these chi particles living off of the Boltzmann tail of their distribution. Okay, so the early universe is a thermal environment. So this process can happen by living off of the tail of the distribution. So let's see how this works. So let's look at the Boltzmann equation. Okay. So the Boltzmann equation starts out, okay, so we wrote this yesterday. I have dn dt plus 3nh, where n over here is my dark matter particle. Okay, so I'll add a little sub-index chi. And now we have to take into account, now we have collision terms. So we have to take into account both that forward process and the back reaction. So let's start by just writing them out explicitly. So let's start with the forward process where chi's are annihilating. So I'm removing 2 chi's, so that's minus n chi squared. And the strength of my interaction, let me call that the thermally average cross-section for the chi goes to phi. Okay, so that's my forward process. And now, of course, I have to add in the back reaction where 2 phi's are producing 2 chi's. Okay, so now I have a plus sign. I have 2 phi's that meet each other, so I have n phi squared. And these particles, I remind you, we're assuming are in equilibrium. So these are some back particles. And what I have here is my thermally average cross section now for this phi goes to chi. Okay. And the trick that we're going to use is the same trick that we used yesterday of detailed balance. Okay, because in equilibrium, detailed balance tells us that nothing should be changing. And so in equilibrium, our right-hand side of this equation should vanish. In equilibrium, the right-hand side should equal 0. Okay, and so what this tells me is that if I want to think of how am I going to parameterize this forbidden process, this 2-to-2 cross-section, the thermally average cross-section in the regime that's forbidden, well, I can write this in terms of my ordinary cross-section, sigma v phi to chi, which is an ordinary cross-section that's not forbidden, times, and what I get from this right-hand side is that I just have the ratio of my number densities. So I have n phi equilibrium squared over n chi equilibrium squared. Okay, that's what detailed balance gives me. And the reason that this is great is because this cross-section, as we just said, this cross-section over here is just an ordinary cross-section. So I know how to parameterize this. There's nothing forbidden and quirky going on over here. This I'll just parameterize like before as an alpha squared. I'll call it alpha effective squared again over massive dark matter squared. Okay, again, a choice of parameterization to parameterize our ignorance. And so using this, let's now plug everything back into our Boltzmann equation and see what we get. So we have that dn dt plus 3hn equals, I'm going to pull out this common factor, this green. So this is going to be the cross section, okay, that we're going to be using. I'm going to write that out over here first. So I have minus sigma v of phi to chi, the direction that's not forbidden, times, now what I have to do is just plug in over here. So I'm going to get n chi squared. And can anyone tell me, what do you expect to happen? What if I have a ratio of number densities in equilibrium? If these particles are non-relativistic, then the number densities are exponentially suppressed. And so what I get in the ratio between these two number densities is an exponent that cares about the difference of the masses of the particles. Okay, so this is going to look like e to the minus, and we have the number densities squared with the ratio. So it's 2 delta m over t minus n phi equilibrium squared. Write that out like this. Okay, so this piece over here, this piece that I just did in pink, this is the this would be the that's this direction. Okay, up here where I'm producing these chi's, that's the ordinary direction. But the direction that we're interested in, where we're going this way, this is our annihilation process. That's now being described by this term. It looks very similar to what we had before with the WIMP. The only thing that's different is that now we have this exponent, okay, that's coming from the ratio of the number densities in equilibrium. So let's take a look at when freeze-out happens. So here's our freeze-out condition. Freeze-out happens when the rate for this process that we're interested in of chi goes to phi is of order Hubble, right? This is always our freeze-out condition. The rate of the process we're interested is of order the expansion of the universe. And now what is the rate of this process? Well, if I'm a chi particle, I have to meet one chi particle. So it's number density of chi. And the only thing that's different now is that it's times the size of this cross-section in the forbidden direction. And the size of the cross-section in the forbidden direction is an ordinary cross-section, alpha effective squared over m chi squared, times this exponent minus 2 delta x, okay, where I've already moved to the dimensionless variable. And now this has to be of order t squared over m Planck, which is, as always, move to x. So this is going to be m chi squared over x freeze out squared times m Planck. But if you just look at this equation that we have over here, and you'll just notice that this is the only difference from the WIMP that we just solved earlier today is this exponent, right? This is really the only difference. From the WIMP equation. Okay? And so similarly, we solve this equation, we solve for m, and here's what we get. What we get is that m chi goes like alpha effective times square root of t equality m Planck. This was exactly what we had for the WIMP, but now we also have this exponent. So we have an e to the minus delta x. Okay? So this is the mass coupling relationship for forbidden channels. And what you see over here is that because of this exponent, we can easily, for the same size couplings, get dark matter masses that are exponentially smaller than the WIMP. Okay, so we get exponentially smaller masses than the 2-to-2 ordinary WIMP annihilation that we talked about. And so thinking of forbidden channels, again, you can think of sort of the mass range that you'd expect to get would be roughly above the keV scale and above. And you see that you really easily get the masses populated on the light side because of this exponential suppression. Okay. Now, just 2 notes about this is that if we wanted to take the Boltzmann equation and properly solve it and ask, how does freeze out look like? It looks exactly like it did for the WIMP, okay? This freeze out picture that we derived looks exactly the same. Okay, so everything stays, this picture that we had where, you know, things were freezing out like this, where we looked at the number density normalized to the entropy density as a function of temperature or x. Freeze out looks exactly the same as it did for the case of the WIMP. And similarly, and you can work this out, if we ask at what temperature is freeze out happening, again, it really just reproduces everything that we did for the WIMP. Likewise, we're still going to get freeze out temperatures with XF of order 20. In other words, dark matter is still freezing out non-relativistically at temperatures that are roughly a factor of 20 beneath its mass. Okay, any questions on forbidden before we move to co-annihilations?
I do have one.
Mm-hmm.
So my question is, it seems like in doing this calculation, we didn't take into account, because I think you're fixing the fact that you want to obtain in the current universe the relic abundance of dark matter. But I don't see where in this procedure you just did, where you consider the fact that since, let's say, the 5 particles are heavier, are heavier, yes, then why aren't these particles going to the psi, let's say? Like, we're not taking into account the back reaction in this equation. right?
No, the back reaction is taken into account. So if you look at the equation that we have written over
Yes.
here, do you see? So in this equation, the pink is the back
Yes.
reaction. Yeah.
Okay.
So
But in the further development,
yeah, so you can, okay, so there are always two pieces. You can fully solve the Boltzmann equation, and as you see, we have taken into account also the back reaction. What's happening over here is that, again, freeze out is still going to be happening. The question is, how instantaneous is your freeze out? Okay, and we're doing here the instantaneous freeze out approximations, and you might find small corrections to this when you, but it doesn't change the big picture. The big picture is still
okay.
that the freeze out is happening. So for the back of the envelope that we're doing, this certainly suffices. But in general, as we work through several mechanisms, you'll see some of them care more about, some of them deviate more from the instantaneous freeze out approximation than others. Okay, but
Okay, so
for
this would be
sort
the,
of,
no, the
yeah, but just
difference then in this case, in which the mass of the psi particle is lighter than the phi particle, the difference is this freeze out, let's say, instantaneous, or
exactly.
it is the only difference. But in general, let's say this curve that you draw, that
Mm-hmm.
history, it's basically the same then.
Yeah, exactly. So for the broad brush picture, this
Okay.
holds, and I'm trying to give you a tool, types of tools for understanding, and this really captures most of what the big picture of the huge differences between these different mechanisms. Okay, getting an exponential suppression is a very, very big deal, right? That really
Yes.
changes the mass coupling relationship, and we're going to see this throughout different examples. How using this back of the envelope technique gives you excellent description of really the big picture differences between things. And of course, when you really want to do something super accurate, after you understand I have something new and interesting sitting here, then you go ahead and you solve it properly. And indeed, you're going to find, interesting for many of these different things, you're going to see, okay, what's happening over here? Is it like this? Is it slower? That also depends on how large the mass difference is, right? If it's very large or if it's very small, things are going to behave differently. But as a broad picture, broad brush picture, this is
The same.
certainly the same.
Okay.
Okay.
Thank you. Yes.
Sure. Okay. So now that we've discussed, so we've done the WIMP, we've done forbidden, and the next one in the 2 to 2 zoo that I want us to work through are co-annihilations. So here we have co-annihilations. Okay. And this is also something that originated sort of in this paper by Greist and Seckel from 1991. And this paper is actually called Three Exceptions, the Three Exceptions paper, and it talks about exceptions to the sort of standard WIMP picture, but it really tried to apply all of those exceptions really very close to the weak scale. And so realizing that this is much more broad than that is really something that's been changing the way people have been thinking. So co-annihilations, let me explain. We drew the picture yesterday, but here's my process. Okay, so we're still within our 2 to 2 zoo. But now imagine that instead of just one dark matter particle, I maybe have many dark particles. Okay, so I'm going to have some tower of particles, and I have chi I and chi j that are annihilating into some other particles phi. Okay, and imagine that in principle, this whole tower of particles can participate at freeze out. Okay, so the whole tower of particles can participate at freeze out. Okay, so here's my sort of, imagine, let's say I have, some spectrum here. Here's chi1. Chi1 is going to be my lightest one, and I have a whole bunch of states going up here to chi n. Okay, and it sort of, I have some spectrum of n dark states. And the lightest one is my dark matter. And so imagine, that all of these eventually, the whole tower is participating at freeze out. But eventually, all of these different particles are going to decay down to dark matter. And so dark matter is the lightest state in this tower, where eventually all of the densities that were sitting in the tower are going to sit there. Okay. Now, in general, if we wanted to properly solve this system, then we'd have to write down a set of n coupled Boltzmann equations for all of these particles in the tower. So in general, described by n coupled Boltzmann equations. Okay, BE is Boltzmann equations. So the trick that we're going to do is we're going to assume, okay, so of course you can only do this when this is true, but the trick is that assume that there's a rapid exchange between the particles in the tower, okay? What I mean by this, assume rapid exchange where chi i's can rapidly change their identity to chi j's, okay? And what this means is that the chemical potentials of mu I and mu j are the same. Okay, so the chemical potentials are the same. And the way that this rapid exchange can happen, we actually don't have to care so much about. It could be that the way that it's happening is that chi i's are scattering and becoming chi j's over phi. It also could be that they're actually undergoing fast decays and inverse decay. So maybe some chi I can decay into a chi j can decay, let's say, into a chi I. Here's a chi I and a phi. Okay, so there are different ways in which this could be happening. We don't even care how, but it means is that our whole tower is in chemical equilibrium with itself. Okay, the tower is in chemical contact with itself. Okay, and in particular, I'm just gonna mention this process over here of this decays and inverse decays. We're seeing it here in the context of co-annihilations, and probably tomorrow we're going to see it in a different context. Just sort of keep that in mind. I'm going to refer back to this tomorrow. Okay, but we have some processes going back to co-annihilations. We have some processes that are giving us rapid exchange between chi i's and chi j's. And so what this does for us is that eventually is that the number densities of i's versus number density of j's can be approximated by the ratio of these number densities in equilibrium. And what this does is then removes n-1 equations for us. Okay, and so what we're going to be able to do now, and this is what's important, is that we're now going to consider. I'm going to write down n, which is now going to be the total number density, summing over all of these particles. Okay, so this is our total number density. Okay, and I care about this total number density because whatever sits in any of the particles eventually is going to sit in the dark matter density itself. Okay, and let's write down the Boltzmann equation for this total number density. And here it is. It's dn dt plus 3nh equals, and it's going to look the following. It's going to be minus sigma effective times v. I'm going to define this in a moment. N squared minus n equilibrium squared, where this, and you can work this out, but what basically sits over here is an effective cross-section, which is a very interesting form. It's summing over i's and j's, where it's weighting number density of I in equilibrium times number density of j in equilibrium times the cross-section for I and j to meet each other, divided by the total number density squared. And so you see that if I ignore for a second the fact that what is this thermally average effective cross-section is some weird summation, the equation itself looks identical to the WIMP, right? This is just 100% the equation that we wrote down for the WIMP. Okay, and so the solution again for freeze out is going to be exactly what we had for the WIMP, where we require sigma to be of order 1 over T equality and Planck. Okay, so that's we got here an equation that's identical to the WIMP otherwise. In other words, ignoring the fact that the cross-section, the expression of the cross-section in terms of the constituents is different. But because the equation is the same, we can just use what we got from the WIMP, which is that sigma effective V should be of order 1 over T equality and Planck. Okay, we don't have to redo it, it's identical. But the reason that this is so important is that you see that this effective cross-section has to be of a particular size. It doesn't tell us anything about the sizes of the individual constituents, okay? And so in particular, the freeze out is happening, it's being populated by, the whole tower is populated at freeze out and then it's decaying down. And the size of our effective cross-section is of order the effective weak cross-section. But this sum that's sitting in the effective cross-section doesn't have to be dominated by the dark matter, okay? And in fact, so it's not just, what you see over here is that the cross-section isn't dominated necessarily by the dark matter by a cross-section that's even related to the dark matter. And in particular, it could be that it's, that your dark matter density, your dark matter amount that we observe in our universe today is set by processes that completely don't involve the dark matter, okay? So the sum, let's just write that out. The sum that enters this effective cross-section needn't be dominated by the lightest particle. Okay, and so in particular, the abundance can be set entirely by interactions of completely other particles. Without even involving the lightest one. Okay? What this means is that our abundance of dark matter can be independent of the interaction strength of the dark matter itself. Okay, so this is really important. It's not just that maybe dark matter is co-annihilating with another particle, but literally the dominant contribution could be from an interaction that doesn't involve the dark matter particle at all. So the abundance can be independent of the interaction of the dark matter. Okay, so this is really radically different than I think what we're typically used to thinking of here. And also just want to note that this is something that that actually also happens in sort of the theory that's the class of theories that's in many ways sort of the poster child for WIMPs, actually also have co-annihilations happening in them. So this happens in supersymmetry. Okay, in SUSY theories. Okay, so that concludes what I wanted us to go over in the context of giving you some sense of different varieties inside the 2-to-2 zoo. Are there any questions about this before we break?
Yes, could you repeat the last bit you wrote in black? So just after writing the sigma effective V equals 1 over T equality over the black mass.
Yeah. So I said that the sum that's entering this effective cross-section doesn't have to be dominated by the lightest particle. Okay, and so in particular, what that means is that the abundance can be set entirely by interactions of completely different particles without even involving the lightest one. Okay, so that means that our abundance, which is set by a size of an effective cross-section that equals 1 over T equality and Planck, can be completely independent of the interaction of the dark matter itself.
Okay, great.
Okay.
Thank you.
Okay, so this is a great point for us to break. So let's. I went a little past time, so if it's okay, let's reconvene at. Well, for me it's 12:03. I guess for you guys it's 11:03, and then we'll start talking about some. Thanks everyone for joining back. So we've now concluded our exploration of the 2-to-2 zoo, and when at the very end of this lesson, I'm going to add to this to the whiteboard a few more references for some other 2-to-2s that we haven't covered, and other interesting ideas that we're not going to be going in detail. So when you see the whiteboard notes posted on Slack, those should already include a few more references for some interesting stuff. But now that we've done our 2-to-2, let's start moving to other types of processes. And the first one that we're going to start with is 3-to-2 processes, and in particular, these are going to be what I'm going to call simps. So we're going to delve into these, and I'll just say a good reference for this. So this is a paper that I put out together with Kuflik, Volansky, Jay Wacker, in a PRL that is 1402.5143. And I really love this work because this work actually originated on the beach, okay, on the beach in Tel Aviv. So I'm a strong believer that I do my best physics when I'm really happy, and I really feel like you should enjoy any opportunity that comes your way, and even at places that are not just sitting at your office thinking about physics. I think you can do excellent physics also in other locations. So highly recommend it. And this was a really fun project that we developed on the beach in Tel Aviv. So let's talk about what happens here. So imagine that we have some nearly secluded dark sector, okay? And our dark matter is going to be the lightest state in this dark sector. So dark matter is going to be the lightest state in a nearly secluded dark sector, okay? And the question that we sort of asked ourselves is, what if, you know, everything that we've spoken about so far involved dark matter annihilating into, interacting with other stuff, okay? And you can ask yourself the question, what if what's most important isn't how dark matter speaks with other particles? What if what's most important is how dark matter speaks with itself, okay? What if what's most important is how dark matter interacts with itself? This is the question that we asked ourselves. And so the idea here is that we're going to talk about self-interactions of dark matter that are going to set the relic abundance. So self-interactions of dark matter are going to set the relic abundance. Now, the first process that you might think of doing is two to two processes, right? So go to the same picture that we've drawn so far, except now I don't have chi going to something else. I just have chi's. I'm talking about self-interactions. So chi going to chi, except this process is a process that doesn't change the number of chi particles, right? So this doesn't change the number density of chi particles. So this isn't going to work. And the first process that does anybody want to guess what it is? I've already written out the answer. It's 3 to 2 self-annihilations. Okay, so I'm going to have 3 chi's that meet each other, chi, and chi, interact through some way, and shoot out 2 chi's. So these are going to be 3 to 2 self-annihilations of dark matter. Okay, this is the first process I could write down that will give me, within self-interactions of dark matter, a change in the number density of dark matter. So we're going to be able to derive a freeze-out mechanism from this. And I'll just note over here that, of course, if I'm talking about 3 to 2 annihilations, then the dark matter can't be a fermion. Dark matter actually has to be a scalar over here. So this is just a side note that dark matter is a scalar, or at least not a fermion for 3 to 2. Okay. So let's look at this 3 to 2 process. And using our machinery that we've developed, we're going to use our estimating tools to understand what's going on. So let's use our estimating tools. Okay. Now, we're going to do the back of the envelope estimate for this. I'm going to write down for you also what the Boltzmann equation looks like, and we're going to understand in a few minutes how I've reached this Boltzmann equation. Okay, but we're going to do, we don't need to write down the Boltzmann equation in order to do our back of the envelope, but just for completeness, let me write down the Boltzmann equation. So it's the NDT plus 3NH, and this is going to be, you're going to see this weird object here, minus sigma v squared of 3 to 2. I'll explain what all of this is, times number density of dark matter cubed minus n chi squared, n chi equilibrium. So this is just for completeness, but we're going to understand how this Boltzmann equation arises in a few minutes. Okay, but what we're going to do now is, using our estimating tools, figure out when freeze out happens. So freeze out happens when the rate of the process that we're interested in freezing out is of order Hubble. Right? So in this case, that would be the rate of this 3 to 2 process is of order the expansion. Okay, let's go through our left-hand side and our right-hand side. So what is the rate for a 3 to 2 process? To remind you that I always ask myself, there are always going to be 2 factors. The first factor is, who do I need to meet in order for this interaction to occur? So I'm a dark matter particle, and for this process to happen, if I'm here's me, and this red dark matter particle over here. I need to meet two dark matter particles, right? So what I'm going to have as my first factor is going to be number density of dark matter squared. Okay. So this is that first factor. Okay. So this one over here is coming from the fact that if I am a dark matter particle, I have to meet two. Need to meet two. Okay. Now the second piece is, of course, that the rate is also going to depend on the strength of the interaction. And so the strength of this weird interaction, I'm going to denote in the following way. That's going to be sigma v squared of this 3-to-2 process. Okay, this is my thermally average cross section, stands in for that big collision term piece that we have, the matrix element for this process squared times integration over the phase space. Okay, so this piece over here is our interaction strength. And just in terms of notation, you see that I've used this v squared over here. So that's kind of just inspired by this v squared is inspired by the fact that if I think of like the flux of dark matter particles that has to hit me in order for this to happen, it's going to be really n times, if you think of it, it's not really n, it's n times v, that's the flux squared. Okay, so this is just, but again, this is just our standard or stand-in notation for everything that really sits in that ugly collision term, which we could write out in detail. Okay. So my rate is proportional to number density squared times thermally average 3-to-2 cross section. And what is this? What is the size of this cross section? So just to write that out over here. So my sigma v squared of 3-to-2, I'm going to parameterize it in the following way. Okay. And this is going to be a little weird. So it's going to be an effective coupling cubed over mass of dark matter to the fifth. So in terms of dimensions, this is correct. And we're going to see exactly how we figure out these dimensions in a few minutes. But for the moment, just believe me. And you already even just see that if I look at the dimensions of my rate, the dimensions of rate, which has to equal Hubble, should be mass dimension 1. Number density squared has, each number density is dimension 3. So squared, I have 6. So obviously this thermally average 3-to-2 cross section has to have dimensions -5, okay, just so that everything makes sense. But we're going to see alternative ways to figure this out as well. Okay, so this is my weird parameterization for this kind of weird object, this 3-to-2, 3-to-2 processes are less familiar, something that we deal with less in particle physics than 2-to-2. But this is a way that we can parameterize it. And now what I do is I take this rate and we're going to use the dark matter number density at freeze out that we've already related by redshifting to T equality earlier today, that we've related to measured quantities. So we're going to take our n chi at freeze out that we wrote earlier today from our redshift to T equality trick. Okay, so I remind you what we had over there was that n chi at freeze out went like T equality m chi squared over x freeze out cubed. That's what we derived. That was the first thing that we derived together today. Okay, so I'm going to use this and just plug this into my freeze out condition that's sitting up here. Right, here's our freeze out condition. Okay, so let's do that. And here's what we're going to get. So I put all the pieces together. So I have so my rate is number density, starts with number density squared. So I'm going to have T equality squared m chi to the 4th over x freeze out to the 6th. That's my freeze out density squared. Then I have times my cross section, which we said we were parameterizing as some effective coupling cubed over mass of dark matter to the 5th. And now we're going to require that this is of order Hubble, which is T squared over m Planck, or alternatively mx squared over x freeze out squared times m Planck. And now all I do is shift around and solve for m as a function of alpha. And what we now find is that the mass of dark matter goes like this alpha effective, the self-interaction strength of the dark matter, times T equality squared m Planck to the 1 over 3 power. Okay, a very different scaling than what we've seen so far. And if I plug in numbers, this roughly goes like alpha effective times around 100 MeV. And so what you see is what we've gotten over here is until now, anytime we've worked through, we've had this geometric mean between T equality and M Planck. What we have now is sort of a generalized geometric mean. A generalized geometric mean between M Planck and T equality, okay? And now it happens to be the case that if this alpha effective is of order 1, is of order a strong coupling, then the scale that emerges is the strong scale, okay? So if alpha effective is of order a strong coupling, then now the strong scale emerges, okay? And so instead of a weakly interacting massive particle, what we now have is a strongly interacting massive particle. Or instead of a WIMP, what we now have is a SIMP, okay? And again, this is just a coincidence of scales, but inspired by the WIMP miracle, this is what we call the Simp miracle, okay? And what you see is that what we have over here is a completely different scaling relationship. We get much lighter masses than the WIMP, and very, very different interactions, okay? This is true not just compared to the WIMP, but of course compared to any of the processes that we've discussed so far. So we get much lighter mass than before, again, for similar sized couplings with very different interactions. Okay, so it gives us light dark matter that's strongly self-interacting. And if we were to work out the freeze out picture, again, we would actually get a very similar freeze out picture where, you know, that's sort of that standard picture that we're talking about. Of course, you could ask yourself, what about the temperature at which this dark matter candidate is freezing out? And not surprisingly, it still comes out to be of order, temperatures of order 20 beneath the mass. So let's just see how that happens. So let me show you that X freeze out is still of order 20, and it's still freezing out when it's non-relativistic. So how can we see this? So remember, we're talking about number density of dark matter, which goes like mass times temperature to the 3/2 e to the minus m over t. That's a non-relativistic number density. And so what we now have in our freeze-out condition isn't n chi, but rather n chi squared. So n chi squared is going to go like mt cubed e to the minus 2m over t. And when I write down my freeze-out condition, which is n chi squared times this thermally averaged 3-2 cross-section, you know, I'm still going to have this exponent that's sitting over here comparing to Hubble. Okay, so because of this exponent, we're going to get in exactly the same way. You know, you get X freeze out that's logarithmic in the couplings, maybe with like a different order 1 coefficient. Okay, so it's still going to be logarithm of the parameters, still of order 20. Okay. So many things that were viable for the 2-2 mechanism just really maintain the same for all of the different freeze-out mechanisms, but the mass and the coupling are, of course, very, very different, and that's going to be crucial for understanding what type of signals and signatures one can expect to have for these different types of ideas. So this was what happens for 3-2 interactions, and now I'd like us to sort of walk through more generally n-2 interactions. Okay. Let's look at n-2 interactions. So, you know, when would I care, for instance, about going beyond 3-2? Well, maybe, you know, maybe dark matter is a fermion, in which case I can't have 3-2 interactions, or maybe there's some Z2 symmetry within the dark sector, which prohibits 3-2 interactions to happen. So it's good to think of also of understanding higher point interactions. So just to mention this, so maybe there's a Z2 symmetry, or maybe it's fermions. In all these cases, you know, you can't think of 3-2 processes. And so let's look at a general case of n-2 self-interactions. So here I have, you know, 1, 2, down to n particles that are going to 2, and these are self-interactions. Okay. And so in general, I'll parameterize the weird object, the thermally averaged cross-section. It's not really a cross-section because it's not a 2 to something, it's an n to 2. But I'll parameterize this thing that's going to enter our Boltzmann equation that's going to determine our freeze out as sigma v. I'm going to call it n minus 1 of the n to 2 interaction. And I define this as some coupling to the power of n divided by the mass of the dark matter to the power of 2 plus 3 n minus 2. And now we're going to see how we get this, this type of parametrization. Okay. So let's use our the trick that we've been using throughout, which is detailed balance. Okay, so see how. Detailed balance. Okay, so detailed balance tells us that the forward rate is equal to the backward rate in equilibrium. So forward equals backward when we're in equilibrium. So let's look at what this looks like. Okay, so for the forward process, what's going to sit in my Boltzmann equation, in my full Boltzmann equation, is going to be n of dark matter in equilibrium to the power of n, because n of these guys are meeting each other, times this weird thing that I don't know what it is, sigma v to the power of n to the n to 2 process. Okay, and then I have to take into account minus the back reaction, where just 2 particles meet each other, so that's n equilibrium squared, times the cross section of the 2 to n process to happen. And this has to equal 0 in equilibrium. Okay, so let's just walk through what this means. So let me now solve for sigma v n minus 1 of n goes to 2 for the thing that we don't understand, that's not an ordinary cross section that we're familiar with. And so this just equals n equilibrium to the power of 2 minus n, the ratio of the equilibrium number densities, times sigma v of the 2 to n process, which is just sort of a regular process. And so now let's look at the dimensions that we have over here. So here are my dimensions. So each n equilibrium is dimension 3, right? I'm talking in natural units, so all I care about is mass dimension. So it's dimension 3, but I have it to the power of 2 minus n. Okay, so that's sort of my my mass dimension for this. And then my 2 to n cross section, this is just a regular cross section, right? So this is just dimensions minus 2. Okay, so overall, this has mass dimensions that should be, minus 2 plus 3 and minus 2. Okay, so this is how we figure out this mass dimension is what feeds into writing down the dimensions of this weird object, the n to 2 thermally average cross section. Okay. Oops. There we go. Okay, and as I said, the alternative way to understanding what the dimension is by looking at that freeze-out condition, and just from the freeze-out condition, if we write down properly the number of number densities that we are proportional to, we're similarly going to get, of course, something that's consistent. Okay, in other words, by knowing how many particles we need to collide with, we can also figure out this this dimension. So this is how we figure out how to write this this weird object. And I'll show you in a moment. We're going to see also a toy model. It's kind of going to explain how we typically decide what power of coupling to put in this parametrization. But of course, once you have a particular model, you go ahead and you write everything in terms of the parameters of your theory, and there's no uncertainty in that sense. So this is just a parametrization of our ignorance at this stage. Okay, so let's figure out when freeze out is happening for n to 2. So here we go. The rate of n to 2. So if I'm 1 particle, I have to meet another n minus 1 particle. So I'm proportional to number density of dark matter to the power of n minus 1. And I'm proportional to the strength of my interaction. So that's sigma vn minus 1 of the n to 2 process. And this should be of order Hubble for freeze out to happen. And so we use the exact same trick where we use the n chi at freeze out. And I remind you that each n chi, okay, and this is the only thing that we need to remember, that each power of n chi at freeze out had 1 power of t equality, okay? So I have here n minus 1 powers of n chi that are entering, and so it shouldn't be surprising that if I work through this, what you'd find is that the mass of dark matter goes like that coupling to t equality to the n minus 1 times m Planck. There's only one of that coming in through Hubble to the power of 1 over n. So this is truly a generalized, this is sort of the full generalized geometric mean in this case. And we've seen what type of numbers we get if n equals 3. Let's work up one more. What happens if we go, for instance, to n equals 4? So for instance, if we go to 4 to 2 processes, n equals 4, then what we're going to get is that the mass of dark matter goes like alpha times around now 100 keV. Okay? And so as we're going to learn together a little later in our lectures, it's difficult to go sort of below the much below the keV scale for this type of dark matter. So there are problems with, and especially actually going beneath the MeV scale when we have to talk about kinetic equilibrium. So it's a little more tricky to start going to this, at least at this simplistic level, to go to these higher point interactions. Though there are ways to work through this as well. Okay. Now, the last thing I want to say about this is just sort of to mention that, of course, n to 2 processes are less familiar than 2 to 2. Than 2 to 2 processes. Sorry, 2 to 2 processes. So let me just give you an example of a toy model. Okay. That would give you, for instance, 3 to 2 interactions, and it sort of serves, at least at this point, as a toy model that's a proof of concept that you can write down such theories. And later we're going to see, that's what we're going to do now, write down a toy model. And later together we're going to see really sort of when we talk about dark sectors, we're going to really see a proper full theory that would admit this behavior, not just a toy model. But here is the toy. So 3 to 2 toy model is the following. Consider, for instance, a Z3 symmetry. Okay, so imagine that I have a single scalar phi. Okay, and it's charged under this Z3 symmetry. So in principle, I could have interactions that look like chi cubed, and I can also have interaction that looks like an absolute value of chi to the 4th. Okay, and so this gives me, as my building blocks for interactions, it's going to give me, I'm drawing here solid lines, even though it's a scalar. These are not fermions. It's just for ease of writing. So I have here either 3 chi's, or I have, a vertex that has 4 legs. Okay, and I can think of different ways to glue these guys together to get 3 to 2 interactions. So let me show you how I get here 3 to 2 interactions. Does anybody want to try to figure out a tree level diagram that gives us 3 to 2 interactions here? Okay. Yes, Sergio.
Yeah, we could glue the, for example, the 4.1 with the 3.1.
Okay, great.
3 coming in and 2 out.
Right, so here, let's do 3 like this. Here's my 4-leg interaction, and then voila. Okay, excellent. Does anyone have another idea? This is great. There's another one we can draw. Okay, nice. There's somebody who's attempting to show me with 3. Okay, great. So what I can also do is take 3 3-point interactions and glue them together. Okay, so I have here's 1, 2, 3, 1, 2, 3, going to 3 here. Okay, so in this case, let's just work over here. What I have is 3 3-point interactions, right? So this is 3 vertices. Okay, and this is actually sort of the inspiration for the fact that when we talked about the 3 to 2 cross section, we parameterized it as a coupling cubed. Okay, so this is just the inspiration for the parametrization alpha cubed for that cross section. Okay, and over here in the second diagram, indeed, we just have 2. We have 1 4-point and one 3-point interaction. Okay, so you can either do 3 3-point or a 3-point plus a 4-point. Okay, so that's a very simple model that already would give us these types of couplings, these types of interactions, and so in principle, this type of freeze-out mechanism. Are there any questions about the 3 to 2 so far? before I tell you how I've been cheating you? Okay. So let me tell you how I've been cheating. I've been doing a very, very big cheat. Does anybody, now that I've told you I'm cheating you, does anybody know how, does anybody have an idea how I could have been cheating right now and everything that we just did? So if you notice, when we did this back of the envelope estimate, I've implicitly assumed that I had one temperature that I could write down that governs the entire system, right? There was only one temperature that ever appeared here. I didn't say anything about multiple temperatures, anything weird. So we've implicitly been assuming one temperature for the entire system, right? Now, if you go back to this 3 to 2 process that I wrote down, what happens if I have a 3 to 2 process? This process is pumping in heat, okay? Because if I have particles that are coming in here, 3 are coming in, the 2 that are shooting out are each more energetic, okay? So I'm really pumping heat into this system. So 3 to 2 pumps heat into the system. And so there has to be a way, if for what we've discussed now, and if indeed we pump in heat, there are issues with structure formation, and we're going to see what happens a little later, either today or maybe early tomorrow, what happens if I can't pump out this heat. But for everything that we've discussed today, there has to be some way for these particles to cool. So 3 to 2 interactions, which so far the only thing that we've accounted for, are pumping heat, and there has to be some way to cool. There has to be some way to pump that heat out, or said another way, there has to be some way to dump the entropy into other particles. So we need to be able to cool to dump entropy, okay? And so the way that we could do this is by pumping heat or dumping entropy into some other light state or standard model particle. Okay, so this can be either to another light state or into the standard model itself. Okay, so so let's say we want to exchange. We have to have this heat exchange. So we're going to exchange heat with the standard model. Okay, so here's the image. There's sort of the picture I want you to take. Okay, so we want to be able to cool. Okay, so for instance, like how can I do this? I can scatter. I can have my chi's scattering off of standard model particles. Here's my standard model particles. Okay, so I want to be able to cool while this 3 to 2 process is happening. I want to be able to scatter off of standard model particles. But of course, if this process is active while freeze out is happening, then I have to worry that what else might be active. I can take this diagram, and much like we did yesterday, I can rotate it on its side. Now I rotate it on its side, and voila, I'm back to that WIMP annihilation of 2 chi's annihilating into other particles, okay? So the big question is, can I cool but not annihilate? Because if this annihilation process is active during freeze out and is dominant, then I'm in big trouble, because then the ordinary WIMP takes over and then we haven't done anything new, okay? So we want to be able to cool without annihilating. And the big question is, can this be done? And a priori, you'd think that the answer is no, because if I think of sort of the size of the thermally average cross sections for these two processes, well, they're really pretty much the same. It's literally the same diagram that I've just flipped on its side, okay? And so just from that perspective, you think that we're going to be in trouble. But if there's one thing that I hope you've learned so far, is that when I talk about rates, rates are not just proportional to cross sections, rates are also proportional to number densities. Okay, and so if we want to talk about this cooling process, then the rate for the kinetic, well, it's true that the rate for the kinetic term, for the kinetic, this kinetic equilibrium, this elastic scattering term, and the rate for the annihilation are both proportional to some thermally average cross section, which is roughly the same between the two. Rates are also proportional to number densities. And so in the first case, when I'm a Over here, if I'm a dark matter particle and I need to cool, then who do I need to meet? A standard model particle. And so the rate is proportional to the number density of the standard model particles I'm interacting with. Whereas for the annihilation, if I'm a dark matter particle, then I have to meet another dark matter particle. And so my rate is proportional to the number density of dark matter. And so if we want to cool and not annihilate, then what happens? So can it be done? Can we cool without annihilating? And the answer is yes, because if I look at the ratio between the annihilation versus the kinetic process, then the ratio roughly goes like the ratio of the number densities of dark matter versus standard model particles. Now the dark matter, as we saw, is non-relativistic when it's freezing out. Non-relativistic means that its number density is exponentially suppressed, okay? And so if we're scattering off of abundant standard model particles, off of relativistic standard model particles, particles that are abundant, whose number density is not suppressed, then we can naturally get an exponential suppression of the annihilation rate compared to the cooling rate, okay? And so if we scatter off of light standard model species, such as photons or neutrinos or electrons, then the number density of the standard model is very large. There are many of these, they're abundant, while the number density of dark matter is suppressed. And so we can cool without annihilating, okay? So, so this, this comes out, I think, like 10 to the minus 8, which is, importantly, just very, very small. And so we can be happy that what we did is actually kosher, okay? So that's gonna be the key. We're gonna scatter off of light and thus abundant standard model species, okay? So electrons, photons, or neutrinos. And so combined, we've now arrived at a set of conditions that has to hold in order for this whole picture to make sense, okay? So here it is. Here are our conditions. So on the one hand, I want the kinetic rate compared to the 3-to-2 rate to be, at the time of freeze out, to be large. I want the kinetic equilibrium, the kinetic process, the process in which I'm dumping my entropy, to be active when freeze out is happening. But at the same time, I want the annihilation rate at the time of freeze out compared to 3-to-2 to be suppressed, okay? And so if we just parameterize this, let me parameterize, let's take actually a different color here. This cross section that we have sitting here for both the kinetic and the annihilation process, the rate of interaction, the cross section of interaction between the dark matter and the standard model. Let me parameterize that. Parameterize the Simp standard model interaction, whether it's the sigma v for the kinetic process or the sigma v for the annihilation process. I'll just call this epsilon squared over mass of dark matter squared. And epsilon is already insinuating that this is going to be a small parameter, so it's enough to have a very, very weak portal speaking to the standard model. So sort of from the picture that sort of is, here's my dark matter sector, and here's my standard model sector, and there's going to be some portal between them. The size of this interaction is epsilon. Okay, let me write that. Let me write this epsilon in the same way, not curly epsilon this way. And so we've now arrived at a range of couplings at epsilon such that everything makes sense, okay? So we have a range of epsilon where everything works, okay? And here it is. So there's some curve, I'll call it epsilon min, which is the minimal value of epsilon for thermalization to happen, for entropy dumping to occur. So this goes like alpha effective to the power of 1/2 T equality over M Planck to the power of 1/3. And similarly, there's a value epsilon max that epsilon should not exceed, where the WIMP would take over. So this goes like alpha effective times T equality over M Planck to the 1/6 power. Okay, and so just to sort of put this in a visual, so here is some plane now of epsilon compared to the mass of dark matter. And here are my two curves, epsilon min and epsilon max, okay? So what happens is that here's epsilon min and here's epsilon max, okay? So if epsilon is too small beneath epsilon min, this is a region where we have no kinetic equilibrium. We're not able to shed the heat, no good. If we're above epsilon max, we're in a regime where 2 to 2 annihilations take over. So this is where we get 2 to 2 annihilations, in which case we're back to the case of the WIMP and we haven't done anything new. But in between this range of epsilon min and epsilon max, this whole range over here, in between, this is the range in which the conditions are met. And this is the range in which SIMPs can emerge. And to give you a sense of sort of the types of numbers that you get over here, so let's say if my MEV, if my masses of dark matter are between the MEV and let's say the 100 MEV scales over here, then you know, this epsilon min over here is, let's say, 10 to the minus 11, and sort of maxes out over here at around 10 to the minus 9, and it goes all the way up to sort of 10 to the minus 5 over here. Okay, so there's a broad range of the parameters such that everything works, and then what we do have successfully is 3 to 2 annihilations that are governing our interactions. We get light, strongly coupled self-interactions of dark matter, and simultaneously we've been able to shed our heat and to cool, and so the picture is consistent. Okay, and also just to mention this over here, that of course as long as epsilon is in this range of epsilon min and epsilon max, then its precise value doesn't matter. Okay, it's not entering our Boltzmann equation in any meaningful way. It's just serving as a way for us to shed that heat, and everything that we've described, again, just depends on the size of that strong 3 to 2 or n to 2 self-annihilations of dark matter. Okay, so as a leeway to what we're going to be working on together tomorrow, just sort of to summarize what we've seen now for SIMPs. So for SIMPs, we saw actually, putting this together, we really have two knobs, two processes. Okay, we have this 3 to 2 self-annihilations of dark matter. And we also have this very important process where dark matter is elastically scattering off of other light abundant particles. Okay, and for the SIMP, as we've just derived, this process, the process of the 3 to 2, is the process that's setting our relic abundance, and it's going to decouple first. And importantly, the elastic scattering that we've just drawn here on the right is going to decouple second. And what I mean by that is that we wanted it, right? We've worked hard to have it active during, well, not worked hard, but we've derived conditions so that it's active during freeze out. Okay. Now you could ask yourself, and this is what gives us the SIMP. You could ask yourself, what happens if the order between who decouples first or second is reversed? Okay, what happens if the order is reversed? And if the order is reversed, we're going to end up with a very different dark matter candidate, which we're going to learn about tomorrow. But before we get to that, what we're going to be starting our lesson with tomorrow is working our way first via cannibals. Okay, so that's all I wanted us to work through together today. Are there any questions?
Yeah, I have one.
Mm-hmm.
So to make 3 to 2 annihilation possible, we implement some triple coupling, but in classical field theory, I think the pi free coupling is something dangerous because of stability. I heard this from something familiar. So how could we implement something such coupling like high cubic coupling?
Right. So so first, just to note, The terms that we wrote down are completely renormalizable. So it's a renormalizable Lagrangian. This follows the rules of, when we perform model building without having to worry about what is my UV completion. I have phi cubed. I can write down a chi cubed interaction. I can write down a chi to the fourth interaction. There isn't an issue with that. What we're going to see together either tomorrow or on Wednesday morning, either tomorrow or on Thursday morning, is actually we're going to work through dark sectors, and we're going to see, this was again just a toy model to sort of show as a proof of principle that I can write down a theory and I can get these types of interactions. But what we're actually going to see is that it's way more generic than that. We're going to see theories that just naturally admit 5-point interactions. So I'll give you already like the spoiler for that. QCD has 5-point interactions. We're going to use QCD-like theories as very rich and beautiful dark sectors that actually naturally are a playground for simps to emerge. But that's stay tuned for tomorrow or Thursday's lesson.
Thank you.